we are on to Unit 5, and this is rotation. Rotation is a huge topic. There are 1,000 little things inside that, but they're all very familiar. They're all very much like linear topics that we've already covered. Let me show you what I mean. If I've got a wheel like this, and maybe that wheel is on an axle, and so it can spin. Well, I can look at some point on the wheel right here maybe, and that point is going to be some distance from the center. Call that R. As the wheel spins, that point moves around, and it comes back to where it was. We start to have a problem when we try and describe this point in terms of our rotational kinematics, or in terms of our linear kinematics. We need rotational kinematics. If we talk about how far this has gone in a full circle, the total distance that we've traveled is going to be 2 pi r. Well, what if we take this thing and we only do a half circle? Okay, well then it's a half of a 2 pi r. Or a quarter circle, we get a quarter of a 2 pi r. What we're looking at is a circumference and then taking just a part of that. Now a full circle is 360 degrees, and in math terms we can express an angle in units of degrees, or we can express an angle in units of radians. 360 degrees we are going to say is 2 pi radians. Now this kind of messes people up early on because pi seems like, what are we doing with this? Why is there this letter in here? What the heck? It's Greek. It might be a little bit easier to say, you know what, pi is about 3. 2 times 3, 360 degrees is something like 6 radians. Now it's a little bit easier to handle maybe without seeing the actual pi in there. So then what we're doing when we do a circumference, when we do any part of a circle, we are really saying that the distance that we travel is going to be an angle times r. What I mean by that, if we travel from here to, let's say, the opposite side. So we're going to go here, out to this spot, and we are traveling on this path. The distance that we've covered, and maybe now because I'm moving in a circle I shouldn't call it x anymore, I'm going to call it s for arc length. The distance that we've covered, in this case, it's half of a circle. That's going to be pi times r. If a full circle is 2 pi radians, and I just did a half circle, then I can say that my arc length, the distance that I'm actually traveling, is going to be theta times r, with theta being the angle in radians. So if I look at my picture, theta is right there, that angle. I could say that's 180 degrees, but I want to give that angle in radians, so it's just pi radians. I can make this conversion 360 degrees equals 2 pi radians, or if you like, if you are about reducing things, 180 degrees equals pi radians. If I'm doing a quarter circle, for example, a quarter circle would be 90 degrees. I can say 90 degrees times 180 degrees over pi times pi radians over 180 degrees. 90 over 180 is a quarter, times pi is going to give me pi over 4 radians. If the pi part is problematic or is a hang up for you, pi over 4, pi is about 3/4, it's about 0.75 radians. Not a big deal. If I do this same path, like the same from this location to that location, but instead of staying at that radius, I were to do this out here, out at the far edge, well, I've traveled the same angle, that's still my 180 degrees, that's still my pi radians, but the actual distance that I've traveled is farther because I'm farther out. So at this inner circle with a radius of r, I travel pi times r meters. At this outer radius of some other r, maybe that one's capital R, I travel pi times capital R radians. I can express my distance this way, and it works out well. Gonna keep going. So that's kind of putting together these ideas, and now I'm going to expand this out a little bit. Let's say I have a particle on this wheel and it moves. Let's just take actually the whole wheel itself, right? I have a slice of wheel and it moves from one spot to another. I can say here is my final position and it's equal to my initial position if I'm not moving. So what I'm doing with this is saying I have a slice of wheel. I'm going to pick a spot. So I have a wheel like this. I am more or less marking this line on here, and I'm going to pick a line on here and call it my theta equals 0. So right here, there is my axis. I'm calling this my origin, think kind of like an x-axis, and then anywhere that line goes relative to that. So if I rotate my wheel this far, I'm going to say that I'm going to define as my displacement angle. So theta final would equal theta initial. If we rotate this thing at a constant rate, what I had before with linear terms was that x final was equal to x initial plus a speed times time. Well, I can do that here too. I'm going to say my final position is equal to my initial position plus a rotational speed times time, which means this theta is going to be my angular position, which I give as just an angle, where over here x was my linear position. Omega is going to be an angular velocity. V was my linear velocity. Now at this point, this was my constant velocity motion, but then when I did my linear motion, I also had a moment where I said, let's let this thing accelerate. And then my equation became a little bit bigger. Looked like this. Well, I'm going to do the same thing here. This was a linear acceleration. And so I'm going to add a term here. Where this alpha is an angular acceleration. So this equation, where I had this top line as my kind of equation 1 when I did kinematics, this is now my equation 1 for rotational kinematics. It really is exactly the same. I'm just looking at angular quantities instead. I have that my distance on my circle was equal to r times theta. We talked about that back here. If I divide that by time, distance over time, that looks like a speed. R, let's keep that where it is. Theta over time, that looks like an angular speed. So I get an r omega. Let's take that equation and divide by time. V over t, that's my acceleration. R, we'll leave that alone. Omega over t, that's an angular acceleration. And I get these relations. I can convert between linear quantities on the left and angular quantities on the right by just multiplying or dividing by r, depending on which direction I want to go with it. These are my linear quantities. These are my angular or rotational quantities. It really is a very direct translation. X to theta, V to omega. It's a lowercase omega. If you're used to seeing this one, that's an uppercase omega. So this lowercase. We get these really straightforward relations. X can be replaced in my equations with theta. V can be directly replaced with omega. A can be directly replaced with alpha. And time doesn't care. Time just stays as time. So then where I had these linear equations that looked like this, I will now have theta final equals theta initial plus omega initial t plus half alpha t squared. That was my equation 1. Equation 2 looked like v final equals v initial plus a t. I'm going to replace it with omega final equals omega initial plus alpha t. And then equation 3 looked like this, where I had v final squared equals v initial squared to a change in position. I will instead have omega final squared, omega initial squared, plus 2 alpha change in position. This top one didn't have v final. Now it doesn't have omega final. The second one didn't have x. Now it doesn't have theta. And the third one didn't have time. And now it still doesn't have time. They're the same 3 kinematic equations that we've worked with a lot. They just look a little different because all the letters are Greek. I'm going to keep hitting some details. X had units of meters. V had units of meters per second. A had units of meters per second squared. Now we're going to get radians. Radians per second. Radians per second squared. Math does kind of a funny thing in that radians are a placeholder, so you might also see this as unitless. Seconds to the -1, which is just 1 over seconds, and seconds to the -2. Radians are just a little bit strange like that. They come and go as they please. Of course, then the question is, what does a problem like this look like? So I want to show you that, and I'm going to show you in this same video. I have a wheel, and this wheel has a radius of 10 centimeters. It's going to rotate, or it's going to start rotating. We'll say it starts from rest. It is subjected to an angular acceleration of 1 radian per second squared, and I want to know how long to complete 2 full turns. So I'm going to set up my table. Now, it might be that it's just more comfortable for you to set up the table that we used to set up. So I'll do that first. Especially the first couple times you do these problems, this happens a lot. So I've got those, and now I'm going to make the changes to the quantities that I'm actually working with. Theta initial, theta final, omega initial, omega final, alpha, t. And I have a table. When I am thinking about these problems, again, especially early on in this process, I might just look at it and just kind of mentally ignore the word angular and be able to do this in a way that's really familiar to me. I can put angular back in there, and as I do more and more of these problems, it's going to become more and more comfortable, and it's not a big deal then. But for right now, I'm going to just ignore the word angular. My initial position, I know I can choose wherever I want to be an initial position of 0. So, you know what? My initial position is 0. I'm going to complete 2 full turns. 2 full turns. 1 turn is 2 pi radians. So 2 turns, that's 4 pi radians. Or if you like, if pi is going to be about 3, then this is about 12 radians, if it's easier to think of that way. My initial speed, I'm starting from rest, my initial speed 0. My final speed, I don't know that one. My acceleration, I've got a 1 radian per second squared. And the time, I don't know, but that's what I'd like to know. I might even, when I do these, I see an angular acceleration, I might just kind of quick say, here is my acceleration, here is my v initial, and work with it that way. Turns out for this, how long to complete 2 full turns? Well, the radius of the wheel doesn't matter. This spot over here is going to take the same amount of time to complete 2 turns as the spot on the far edge is going to take. So here we go. I'm going to come up with my kinematic equations, and I'm actually just going to copy paste them from above, because they're a lot to write out. I wrote them really big. I'm not going to copy paste them from above. I'm looking for time. I have all of these things, but I don't have v final. So equation 1 really does well with that, right? Equation 1 would have been x final equals x initial v initial t half a t squared, and I'm just going to convert it. Theta final is theta initial plus omega initial t plus half alpha t squared. And now I'm going to start plugging in. T is what I'm looking for, so let me get that in red right now. And then let's see, theta initial is 0, let's get rid of that. Omega initial is 0, let's get rid of that. So we get theta final equals half alpha t squared. I'm solving for t. So t equals, I'm going to multiply by 2. That gets rid of the half. I guess I can write these, right? That gets rid of the half, but I have to do it on both sides. I'm going to divide by a, or alpha. That gets rid of that. Divide by alpha. And then I'm going to end up having to take a square root. So I'll plug this in. 2 times my final position was 4 pi. Again, something like 12. Over alpha, which was 1 radian per second squared. I'm going to take a square root. If I estimate this as 3, 2 times 12 is 24. The square root of 24 is going to be a little bit less than 5. So let's see what this is with plugging in the 4 pi instead. Because pi is a little bit more than 3, this answer is going to be a little bit more than what I had estimated. I estimated just under 5 seconds. What I get with plugging this in is 5.01 seconds, which is not bad. It's the same process that I had before. If I want to know how fast I'm going at the end of those turns, then I can solve for v final here. I might say, with equation 2, v final equals v initial plus a t, and then translate it. You don't have to go through and start with the linear quantities. If this is clicking for you right away, then just go for it. But if you see all these Greek letters and think, I'm not quite sure what to do with this, this is taking a second, then just do it in the linear terms and translate it. My initial velocity, that was 0. My angular acceleration, radians per second squared, and the time 5.01 seconds. Well, that's easy math. That's going to be 5.01 radians per second. Maybe now I want to know, how fast is a point on the edge of the wheel moving after that amount of time? Now it matters what that radius is. But what I have is that v equals r omega. My radius was 10 centimeters. My angular speed is 5.01 radians per second. 0.1 times that, I'm going to get 0.501 meters per second. This is what I was talking about, how radians just kind of disappear when you need them to. But that's how I would find the speed, the linear speed, or if you like. So this is the linear or tangential speed of the edge of the wheel, or of a point on the edge of the wheel, if you like. But that's it. That's rotational kinematics. Very long video, I know, but hopefully that pulls things together pretty well.